Let's start. I know. So it's that time of the year. 2 more weeks of class. So 6 more lectures. So what that means is that we're getting into the final push. We're going to wrap up chapter 7 today with Rao Blackwellization. This is what I think is the most important stuff in the book, is all that estimation stuff. That stuff we can agree on. Even estimators that are a bit different, maybe asymptotically they're the same, they share some properties. I tend to like penalizing likelihoods in particular ways. So that's my version of doing things, and I have a way of talking about it. So I usually am a Bayesian. Saying that, there's other good things out there. So some Bayesians, they do things like maximum likelihood estimation. So there's a branch of Bayesian analysis called empirical Bayes. And there's kind of this side step where you do an MLE sort of step to figure out which hyperparameters you might want in your prior distribution. So a lot of these techniques can kind of be blended together as well. We're just kind of touching on the tip of the iceberg. There's a lot of good ideas out there. And the name of the game is to explain, where your stuff is coming from and then compare to other stuff. And that's what people that are doing inference and estimation are doing. There's a more contentious branch of statistics, and that's hypothesis testing. So we're going to spend our last 6 lectures talking about this stuff. I don't want to turn you into hypothesis testers. I'm going to try to encourage you not to be hypothesis testers, but when you need to be, hopefully you'll understand the choices that you're making. There's a lot of debate on how to do this. There's some areas where there's not so much debate, and there's some areas where there's so much debate that we'll never solve the debate, and I'll tell you what the debate is about. Basically, people aren't asking the right question, is the way I'm going to say it. That we're disagreeing on what the question is. And so if we understood what the question was and what the technique was actually answering, maybe we wouldn't disagree with each other so much. I've been unsuccessful in the last 15 years of my career trying to make these points. So at least at scale, hopefully I'll get it right this time. There's going to be a lot of holes in this. And I try to go over this a little bit more in my Bayes class where I do a full-blown comparison. So I don't think you can really understand this stuff until you understand all the different relative merits of different techniques. I'll say a little bit about it. But what I'm going to mostly do is go into the Neyman-Pearsonian school of thought, tell you what Neyman and Pearson were doing, tell you that there was a debate with Fisher over what Neyman and Pearson are doing, and it's kind of I would say people are doing most often some butchered form of Neyman and Pearson. And Neyman and Pearson would not advocate what people do. So they've never done it. So people kind of turn what they're doing into this automated procedure, and I don't think it should be an automated procedure. I'll tell you what all the issues are over the next couple lectures. I'll point you in the direction of a couple discussions. The ASA, the American Statistical Association, is constantly having consortiums where people get together and they talk about hypothesis testing. And what should we do to correct everything? And there's usually the frequentist camp and then the Bayesian camp. And they fight with each other. And personally, I find all the politics behind it, kind of an abomination. And so they don't really advocate that well on what we should do. Saying that, I'm a member of the ASA, but I think every single year I'm going to get rid of my membership and never be a member of this body because they can't even settle something that's probably the biggest pressing issue and the biggest black eye in all of statistics. Okay, so at least you know how I feel. I don't love this stuff, but it needs to be talked about. In my Bayes class, I show you some machinery and how you kind of build in some of the stuff that we do into large-scale, high-dimensional model selection techniques. And so model selection, in some sense, is hypothesis testing. But again, what I try to teach in that class is a comparison. So compare, show what the relative merits are of everything, see how it works in simulation studies where you know the answers. I don't think you can really understand all this stuff without doing those comparisons. We won't have time to do it all in this class. Okay, Rao Blackwell. Actually, before I begin, any questions about the midterm? Anything that's just killing you? Everything? So hopefully the first question wasn't too bad. What are the MOM estimators? What are the NLE? The punchline of that question is the MOM is not unique. So you could co-estimate 0 with the expectation in the MOM estimator. And that's probably how you built everything up in the part A of that problem. In the second part of the problem where I say that the mean is 0 of everything, the MOM estimator is still a MOM estimator. It's just not all that efficient because you're co-estimating 0 with the expectation. The NLE says you can't do that, and that 0 is in there. And so I kind of like NLEs because of that. The likelihood is constrained by whatever the conditions on sampling distribution are. I like that. The second problem, I think it was the second problem where we are looking at WX, X bar, plus WY, Y bar. So this is going to be the sum of the XI's. I don't remember if I did N or K on which one. This one's K. This one's K. K goes from 1 to cap K. And this one is sum of the YI's. N?
Yeah.
Wow, I must have really scarred you guys, huh?
Did you get those reads?
So I'll use I and just be totally inconsistent because everybody uses I in there. All of these right here, the XI's are coming from some process. I said they come from this process. And the YI's come in an IID fashion from this process. They're the same processes. So if you recognize this, the question is really, how do you estimate U from this process? But I want you to keep the XI's and the YI's separate. And I'm just imposing some estimator. So these are just weights between 0 and 1. So this is an unbiased estimator of mu. And so in the class of this estimator that's unbiased, what's the Kramer-Rao lower bound? You can work it all out. How do you do it? You just need to write down the likelihood for this function. So the likelihood when you get an x and y, and this is, you get this part right, everything else is just kind of automatic in the problem. It's going to be product, I goes from 1 to n. I'll write down everything, it won't hurt you to do it. Sigma e to the minus 1/2 xi's, oops, this is k. I'll try to be consistent. Xi's minus mu, sigma squared divided by sigma squared times this product. Now, there's a lot of ways you could do this problem. If you wrote it all out in matrix format, maybe that would help you out. If you did something like z is equal to the x1s down to the xk's, cap k, y1 down to the yn's, you might be able to simplify some of your notation. That's probably the way I would do it, is I would set it up as a vector. I know what the variance would look like. In that case, it's just sigma squared times I, and I'd be able to write it in matrix quadratic form and work through everything. But this is what the likelihood is. This is what the likelihood is. Take the logarithm. It's parabolic. Take two derivatives over it. You can figure out what it is. So what the answer is. That's how you figure out the Kramer-Rao lower bound. I said that the answer to this question was obvious, what the best estimator is out there in the unbiased class. What is the answer? If I gave you all this data, it's coming from the same process, it's a little bit peculiar to label it as two different processes. But that's the way we set up the problem. What is the best unbiased estimator in the L2 norm? If you guys don't know this, you've missed example after example after example. Okay, let's just say this. Let's say I have zi's coming from a normal mu sigma squared right here, I'll say you've got I goes from 1 to m. Everything's IID. How would you estimate mu?
X bar.
X, Z bar. So, Z bar. M. You can show this is unbiased, and it's minimal variance. So it is the variance minimizer. You can prove that directly. So just go to which function minimizes the variance of something. It's not hard to figure out. So the variance of something, variance of some function, I'll just call it E, is going to be sum of the zi's minus E squared over whatever. It doesn't matter what I plug in here. But I'll just write down this sum of squares thing divided by n. You could figure out what the best E is. Take a derivative. It's pretty easy to do. Solve for E. You'll figure out what it is. Best E is going to be that thing. So direct calculation, just a derivative. So we already know this is the right answer. So what we really want to do is we want to put these weights so that we're averaging everything. So what is this weight proportional to do it? K. Yeah, so this is going to be proportional to K. So I'll divide it by K plus N. What's this one proportional to? N. Same normalizing constant. So that's the answer. And so if you just knew about normal and you knew that, hey, this is all coming from a normal, the answer is the average.
Okay, but then it doesn't achieve the Kramer-Rao bound.
How do you know?
Like if you take the variance for mu hat. And then
What do you think the Kramer-Rao bound is?
Was it sigma square over n plus k?
Yeah. So the Kramer-Rao bound, CR, is going to be sigma squared over n plus k.
Yeah.
What's the variance here? So I'm going to take my n is going to be n plus k. What's the variance for
But
this?
if you could satisfy like mu hat is equal to, or mu is equal to wx, or mu hat is equal to wx x bar plus wy y bar, and then we calculate variance for mu using those estimates for wx and wy, it doesn't satisfy the.
So that's the average. It's unbiased. The variance of that thing is sigma squared over n plus k.
I do not get that. Like,
What's the variance of that? Variance of z. Bar. You could probably convince yourself real quickly that sigma squared over n plus k. I called this m a second ago. That's what the variance is. The Kramer-Rao bound is that as well. So there you have something that's wrong in your calculation.
Professor, I think even if you go by this,
Yeah,
you
like-
still get that.
No, if you take the weight.
There's tens of thousands of ways to think about this exact same thing. I would say go back, check your work, so we can have a conversation. Anybody agree with Pearl on this?
I was getting some weird stuff.
Yeah.
So it's probably just going through your calculation, working it out. So you agree that the Kramer-Rao bound is that?
Yeah.
You agree that that estimator is unbiased?
Yeah.
You agree that the variance is this?
No.
You don't agree that the variance is that?
I just
Right here?
Okay, I just don't agree with the variance of that term.
Variance of sum of the zi's, I'll call it k plus n. This is equal to sum of the variance of the zi's divided by k plus n squared.
Oh, yeah.
Okay.
I got it.
But if you separately take the variance of wx x bar plus wy y bar.
Still works out.
No, it does not. I tried it. I went back home and tried it.
You just got an n down here that you forgot. If I just look at this, the k cancels that.
But that
The
is,
n cancels that. I'm dividing by k over n. It's the sum. It's exactly this.
okay, that gets squared when you like get it out of the variance term.
I'm going to try to convince you.
And then when you
To-
add that, you
Yeah.
I'm going to try to convince you to pause for a second and go back and check your work.
Okay.
So, I'm as sure as I get. So, I'm never positive, but I'm about as close to positive as I get on this. Go back and check your work. I think all we did was this. This is exactly the same thing. That, for these weights right here, is that. You're going to square them, but you're also going to have the k squared coming out. It'll cancel. Everything will work out perfectly.
Actually.
What's that?
Actually, I went back home and thought about this exact estimate, and then I felt very stupid because I was solving quadratic equations.
So these will get squared outside, so that'll be a squaring there. Squaring there, you'll have this k getting squared when it pulls out. It'll cancel that one. You'll have the n plus k in the denominator that gets squared, but I'm summing things up n plus k times. Everything cancels. It really is that calculation in disguise. So it is just the standard estimator. Here's the fun part. If I change this, let's settle down. So it's just down one. So in disguise. If you have good intuition for this, that's what I do. So I'm allowed my opinion still. Let's do something interesting and just think about this for a second. Let's say I change this to this. What do you think the answer is? If you worked all this out and you did everything, and you matched the Kramer-Rao lower bound for the earlier problem, you would have had this. Sigma squared, sigma squared, sigma squared, sigma squared. And they all cancel each other. So if you work through the Kramer-Rao lower bound, did everything, did all your matching, you should come up with that. You may have factorized out the sigma squareds earlier in the problem. So it would look like this if you ended up having the x's. So everything is getting weighted by the precision of everything. So those are the weights, the precision weights. So that's how that problem would change just a little bit. And it kind of makes sense that if this variance was very large right here, I wouldn't want to put a lot of weight on something. So if the variance was high, don't put a lot of weight on that. So if the variance was small, put a lot of weight on that. And that's what that estimator does. So sometimes I ask this another question where I build these in a little bit differently. But what's kind of nice, at least this is what I thought, and maybe you'll think so next week, that this is intuitive. So what's intuition is experience. So anyway, the answer to that problem is the average, the straight up average. Any other questions? Complementary? So unhappy. Okay. I won't explain any of this stuff anymore. Still can do a few more review sessions. Try to build this stuff up, but again, this is just practice. So if you had worked through the Kramer-Rao lower bound for just mu in a normal distribution, you would have done exactly these same calculations. So you just would have labeled things slightly different. Okay. Rao Blackwell, let's do something easy. So, Rao Blackwell. So it says this. So if expectation of W, this is going to be some estimator, Usually we write this as like EX or something like that, function of the data. So I'm going to imagine that xi is coming from some distribution that has some parameter in there, theta. So it doesn't need to be IID. Nothing is specific about IID in this problem. So I'm just going to call this some estimator. In the way the book writes it down, is they say that it's an unbiased estimator of tau theta, some function of theta. So W is an unbiased estimator of tau. So we see that sort of stuff all the time, like with variance or something like that. A lot of times people build an unbiased estimator of sigma squared and not of sigma. Why? Arbitrary choice. Okay, this is what Rao Blackwell says. Rao Blackwell isn't specific about how you got W. It's just some estimator. It has some property. It's an unbiased estimator of some function of theta. So Rao Blackwell says you can always do this. T is a sufficient statistic, so it's a function of the data, and normally I'd write T of X right there, but I'm just using the same notation they present in the book. So this is going to be a sufficient statistic. So Rao Blackwell says, do something with this estimator before you go and use it. So regardless of how you came up with W, Rao Blackwell proposes a new estimator. It's going to be the expectation of W given T. So the notation is specific to this T sufficient statistic. Remember, expectations of things are functions of what they're conditioned on. That's always true. So this is the Rao Blackwellized estimator. They don't say this in the book, but this is what I usually call it. Rao Blackwellized estimator. I won't give you examples here, but I have seen this used in Monte Carlo land. So if you have Monte Carlo samples from something, you can do something and kind of break down variances. I won't tell you all about that. I never really see this done in just inference. So, but I'll discuss what Rao Blackwell is telling us with this. I'll tell you why I don't see people usually do this. But usually this should be automatic if you've done everything right. So here's a fact. So facts. The expectation of our Rao Blackwellized estimator is still unbiased for theta. So I haven't changed any of the bias characteristics. And the variance of theta T, our Rao Blackwellized estimator, is less than or equal to the variance of our original estimator. So it improves variance to do this. So it brings down variance. I'll say a few things about that after we prove this. This is probably the simplest proof in all of the class. So proof. Let's just look at it. So expectation of a Rao Blackwellized estimator is just the expectation of the expectation of W given T. That's what it is by definition. This is the Rao Blackwellized estimator. What are my expectations over? Just in case it's not clear, it's that thing right there, and then I'm going to take expectation over W. So it's the typical iterated expectation formula. And so this thing is expectation of W. Direct application of Foodie's. So you can probably prove that directly just by changing the order of your integration. Show the left-hand side as the right-hand side. You just need to apply Fubini's to do that. So this part is proof. So expectation of W is tau theta. So we haven't changed the bias. And the other part to the proof is just variance of W is equal to the expectation of the, I'll write it over here. Variance of W. My brain and my hand are not syncing. Is the expectation of the variance of W given anything, really. But I'm going to condition on the sufficient statistic. The variance of the expectation of W given. So this part right here is the variance of our Rao Blackwell estimator. And this thing right here is positive. How do we know that's positive, that term? Exactly. So variance is positive, it's the expectation of a positive thing. And so it means that this thing right here needs to be bigger than that thing. So, proof complete. Variance of W is going to be greater or equal to the variance of VT. I never used that T was a sufficient statistic in any of that. So conditioning on something always brings down variance. So including information brings down variance. I kind of like that. So it's a good idea to condition on stuff. Things that you know about, what are you doing when you're conditioning? You're bringing down variance. Think about regression. Why given the x's? I include the x's. What am I really doing? I'm explaining the variance in the y given the x's and showing how much the x's explain the variance. So by conditioning on things, you bring down the variance. That's what we explain to people as statisticians. So how information contributes to variability. That thing alone is what makes you a statistician. That's the important stuff. It's understanding variance. Or stochasticity. So uncertainty. So why does T need to be a sufficient statistic? It seems like it's a good idea to make it a sufficient statistic. We've been talking about that over and over again. So I would say what Rao Blackwell is saying is, if W doesn't include the sufficient statistic, you can build it in automatically by doing that. Doesn't mean it's optimal, and it doesn't mean that there's no other estimator that can't bring this down a little bit further. So saying that, you can't keep applying this. I can't just keep conditioning on the sufficient statistic over and over again. It won't do anything for you. You can only apply it once. Seems like a nice idea, I'll just keep doing it. But eventually, you get that equality term right there. So why does T need to be a sufficient statistic? Seems like a good idea. Let me show you an example. If it's not a sufficient statistic. This example is in the book. Example. T not sufficient. So this is applying Rao Blackwell in just exactly the wrong way. So let's say you have an estimator. Let's just consider two random variables. This could have been more than two. We'll just make it simple. I'll keep the notation the same and say the mean is theta. I usually call it mu. We'll say we know the variance and we'll just call that 1. Let's consider an estimator. So X bar might be good. So estimator. So we know that the expectation of x bar is theta, so it's unbiased. And the variance of x bar is equal to 1/2 right here. So this is just sigma squared over 2. So typical thing. Same exact calculation we're doing over here. So that estimator is pretty good, and we could probably argue that in some sense it's the best estimator. So in the class of unbiased estimators, if I like L2, which means I like variance specifically, that form, then x bar is pretty hard to beat. So if I like those two things. Let's do some conditioning. So we're going to condition x bar on x1. So this is not sufficient. So I'll just point out, x bar's already got the sufficient statistic in there. And so there's no reason to do any of this, but I just want to show you what it looks like if you condition on something that's not a sufficient statistic. So I can call this phi of x1 is equal to that thing. So this is not Rao Blackwellization because that's not a sufficient statistic right here. That's expectation of x1 plus x2 divided by 2 given x1. This is the expectation of x1 over 2 given x1 plus the expectation of x2 given x1, x2 is divided by 2 as well. So same thing. If I know x1, then I know x1. So this thing is x1 over 2. This thing right here is x1 and x2 are independent of each other. Probably should have said that. So x2 doesn't provide any information, so this is the same thing as the expectation of x2 over 2. So that's theta over 2. So if somebody said to do this, they said, you've got x bar. Scotland said conditioning on stuff brings down the variance, which is a good idea, so I'll just condition on some stuff. I've got x1, I'm going to condition on it. So it can't hurt us, right? I didn't change the bias level of my estimator by doing this. That's true. So the bias level hasn't changed, and presumably I've decreased the variance of everything. That might be true. So this component obviously doesn't have any variance to it anymore. So if I said to do this and use this as your estimator, what would you say back? What would be your biggest critique of this estimator? Looks pretty dependent on theta. So I need to use theta to know to use this estimator. So keep in mind what we're trying to do, estimate theta. So if I gave you back that and said, you can use this to estimate theta, I would think you're a lunatic. So just give me theta, it's a better answer. Why am I going to just add some jitter to it? So this is not an estimator. By conditioning on a sufficient statistic, it will not contain theta. So it won't be there. So if I plug the sufficient statistic and the parameter in, if it's sufficient, the parameter falls out. So that's the definition of a sufficient statistic. So if I condition on a sufficient statistic and I have a parameter in there, it's free of that parameter. That was our original definition. So you're thinking about that ratio. That ratio is a constant, not dependent on the parameter. So that's the definition of a sufficient statistic, so you can prove that by definition. So sufficient statistics, conditioning on them makes it so there won't be a theta over here. So what Rao Blackwell would say to do is this in reverse. So if somebody came in and they said, hey, we've got an unbiased estimator of theta. So you've still got this same data. You've got these two things. Statistician walks in and says, I'll build you an unbiased estimator. X1 is my estimator. We'll take that pW right there. And somebody says, why is that a good estimator? It's a good estimator because X1 is equal to theta. So it's unbiased. So this is the thing that I'm trying to put you guys off of. It's just saying it's unbiased, so it's a good estimator. You need more than that. You need to be thinking about variance. Your uncertainty, quantification, that's what makes you a statistician. So that estimator is obviously beatable. You can work this out. Rao Blackwell says to do this. Take X1, your original estimator, and condition on the sufficient statistic. So you could condition on X1 plus X2, and I don't really care if you condition, if you divide by 2 right here, it won't make any difference. So this part's the sufficient statistic. You can work it out both ways, and you'll get the same answer whether you divide by 2 or not. It won't make any difference, everything will, that 2 will cancel. Once you're working through everything, keep in mind, you'll have to work through the conditional PDF of all of this. So you'd have to know your conditional normal forms to work through everything. So this is normally distributed. That's normally distributed. So I could figure out what this conditional distribution is. It's normally distributed, and I can figure out its expectation. I'll let you do that and work through that. If you don't know your conditional normal forms, go back to your regression book, and that's what the whole regression book is about. Those 2 formulas, more or less. This thing right here, what do you think the answer is? Just intuitively. It's X bar. So it will be this. X1 plus X2 divided by 2. So you'll get back the optimal answer by doing this. So it's a little bit silly. The way I think about this, what Rao Blackwell is saying is you should be using a sufficient statistic. If you're not, then prepare to get beaten. So because if you haven't used a sufficient statistic, certainly you'll get a variance reduction by conditioning on it. So my real thing that I think about is why don't you use techniques that always have the sufficient statistic built into it. So that's why mom estimators are so easy to beat, because there's no guarantee that it includes the sufficient statistic. It might. So, but no guarantees. The likelihood always has the sufficient statistic in there. A Bayesian analysis always has the likelihood in there. So whether or not you're a likelihoodist or some form of a likelihoodist, you're going to get this for free, because you're already going to be self-Rao Blackwellizing, because it'll be conditioned on the sufficient statistic. So Rao Blackwell comes in and says, use sufficient statistics. Likelihood-based analyses make that happen for you. That's a punchline that I've been trying to deliver throughout this class. I like likelihood functions. I've never seen this actually applied outside of Monte Carlo techniques to reduce the variance in your Monte Carlo samples. So hard part of it is you need to know the sufficient statistics for your models, which isn't always an easy thing to do. Anyway, enough about that. So that's the conclusion of chapter 7. I'm going to post a few more homework problems for you after I get done with this class. So you'll have a few more, and I'll give you a few more also in chapter 8. You can turn those in at the final exam. So with the final exam, I'm going to give you a take-home final. So really push on some of this material, give me an opportunity to give you some harder problems, a little bit more time to think about it. So I'll say more details about that next week. Okay, hypothesis testing. I'm going to come in next week and I'm going to just read you a bunch of warning statements from the ASA, from this fiasco that happened in the basic and applied social psychology journal, so FAST. So I don't know if you've heard about that a few years ago. They sent a shockwave through the statistical community by banning p-values. So it's a strong thing to do. So not all p-values are built the same. There are some p-values that I think, no big deal. I would do something very similar to that. You say it with p-values, I say it with the posterior probability, and they're equivalent to each other. In some cases, the p-value and the posterior probability, they are not the same, they're not asymptotically the same, and in fact, asymptotically they diverge from each other. And so that's where some of this controversy comes from. I'll tell you more about that soon. Here's the whole game in hypothesis testing. I think you guys have all seen this. So it usually confronts a question that looks something like this. I'm going to have two competing hypotheses. This is called the null. This is called the alternative. Usually what we're doing is we're collecting data and trying to maybe reject the null. So usually you have some problem with some parameters. This is the typical setup. Let's just say x's come from some distribution, so same notation we've been using the whole time, where I've got some parameter theta. You can think of this as a scalar, if you'd like, or you can think about it as a collection of random variables, or a collection of parameters. And I might want to test if they're in some range, right here, theta naught. So this is the null hypothesis. So is theta in theta naught? Here's the question. Or is theta somewhere else? We'll usually call that the alternative hypothesis. So this is the alternative hypothesis. Very reasonable. Compare two things to each other. Which one do you like better, conditional on the data that you've seen? It's a noble rule. So there are some tests that look something like this. I'll just start out with my biggest criticism. And this is the thing everybody is arguing about. So I'll just front load this and tell you what the argument is all about. So very typically, you're going to confront a problem like this. Xi's are going to come from some distribution. Some parameter, theta, is going to be between negative infinity and infinity. I'll just say something like that. And we might want to test if theta is equal to some value versus theta is something different. What's your criticism with this test?
That will be
yeah. I already know the answer. So the answer is no, theta is not theta naught unless you performed a simulation study and you just are playing a magic trick. And you happen to know what theta naught is. In real world situations, theta is not theta naught. So that's all there is to it. So the p-value question, the typical Neyman-Pearsonian unbiased test for checking this right here, and I want to point out the likelihood ratio is non-monotonic in this, and that's where the issue really arises. But if you break it down into a qualitative question, they're asking this specific question. Is theta theta naught? And so if I crank up the data set high enough, I let n get real big. So if this is big, you'll reject. So guaranteed. Even if theta was, so if you played a game, even if theta was theta naught, if you had picked the right value, and I don't believe you, so if you did. So it turns out the typical p-value for testing this is going to be uniformly distributed. And so we'll prove that later. So it means that I'm just drawing from a uniform distribution. So if all of a sudden p didn't duck alpha, and I'll say what all that means soon, I could crank up n, redraw from another uniform distribution, and eventually I will duck alpha, and you'll reject. If theta is not theta naught, that p-value will be decaying exponentially, typically. And so it's really a question of how fast did you decay to a particular p-value, but nobody tests that. I'll say a lot about this, but the ridiculous part of this question is just the question in itself. Theta is not theta naught, and I can already tell you. What people mean to ask is it close? And we need to define what that means. Relatively speaking, are you close to theta naught? That's what all the disagreement is all about. So the Bayesians encode a relative distance. They calibrate the alternative. And so the Neyman-Pearsonian is checking this on a more absolute scale. So it's really a question about the distances they're using to measure this question. Relative to what? They encode it through their prior. And the non-Bayesian is asking this question absolutely. I do think it's the right thing to do is to qualify and say how far away from theta naught would you have to be before you're willing to reject it. The thing that people are unwilling to do because they're cowards is calibrate that and say what they mean. But I think it's not a statistical question, it's a science question. And in every question, it cannot be automated because theta means different things to you. And so you need to come up with relative thresholds. I think you have to. If you're watching Bill Woodall's colloquium a couple weeks ago, this is what he said to do. He never said how to do it. Coward. So I'll say a little bit about that. They're all cowards. It's hard to just answer the question in a math-based class because you need real context to answer that question. Okay, I'll just say a few things about this. So anytime you're going to gauge a question like this, you can make an error in one of two directions. So let's say the truth was it's either H naught or it's the alternative. It's either the null or the alternative. And I'm going to make a decision. So I'll say my decision is either H naught or the alternative. So I'm going to choose between these two things. And I will say, I really don't care if you say fail to reject the null or accept the null. I don't care. It doesn't matter. At the end of the day, you're doing something, you're making a decision. It's not a big deal. Saying that, one is logically incorrect. And we'll talk about what Karl Popper says about this. So if you haven't seen something, you might not know that it's wrong. You just don't have enough evidence for it. We'll say more about that later. But if you say accept or reject, I'm okay with that. So there's two types of errors that you can make. If the truth is H naught and you decide H naught, you're correct. Same thing for the alternative. If the alternative is true and you decide the alternative, you're correct. So this is an error, and this is an error. And these two errors have two different names. You can tell that a statistician named is type 1 and type 2 error. You might be familiar with things like precision and recall. They're not the same as these, but if you give me n, and you give me precision and recall, I can calibrate the type. I can calculate the type 1 and type 2 here. So if you're from a different camp, this is equivalent in some sense to that. They're not the same, but you can derive one from the other. Sensitivity and specificity, those two things that statisticians can't even say the words to, they're all about this stuff. Okay, so they're re-encodings of the type 1 and type 2 here. Okay, so lots of words for the same thing. We're going to be studying this. The first thing the book goes through is the likelihood ratio, and they tell you about it, and then they change all the notation on how they use the likelihood ratio. I'll try to front load that next time. We'll look through a couple examples, and eventually what we're going to prove is that by looking at the likelihood ratio, if I fix the type 1 error rate, keep in mind you've got to fix something, just like the bias variance trade-off. If I make more of this error, I make less of that error. If I make more of that error, I make less of that error. So there's always this trade-off. What Neyman and Pearson do is they prove to you that if you look at the likelihood ratio test for a fixed type 1 error rate, it minimizes the type 2 error rate. So they call that uniformly most powerful. So it'll do it for all thetas. That's the uniform part of the statement. And power is 1 minus the type 2 error rate, at least the limit of it. And I need to tell you what all that is. So we're going to be showing you a schema for minimizing that thing for a fixed one of these. So there's obviously some preference on fixing the type 1 error rate, and you'll hear discussion from people that, well, that's more important than that. You won't hear that discussion from me. I see it as equally important, how you think about these things. But in the Neyman-Pearsonian framework, there's obviously a bias towards the type 1 error rate. We'll talk about a few examples, see if we can justify that. Okay, that's it. So be on the outlook for a couple homework problems. Probably put up 5 or 6 so you can just kind of start motivating yourself through this next sequence of lectures. We'll spend the next 6 lectures talking about hypothesis testing, and we won't go to chapter 9 for intervals. I'll say a few things about intervals. There's just way too big of a conversation to be had about intervals. They show you 1 or 2 different ways to calculate intervals, and I'll make that correspondence, but I'm just going to do it for 5 minutes, and I won't test you on intervals in this class. But I will test you on testing. That's it for now. Have a good weekend.